Now here we talk about what is activation function and types of activation function and its derivative. In forward propagation we can say activation functions play a key role. So generally activation function decides whether a neuron should be activated. And activation functions introduce their non-linearity in the neural network so that model can learn the complex patterns. Here first we can go through with the sigmoid activation function. Here the sigmoid activation function curve looks like a shape and the range of this function is from 0 to 1 and the formula for this sigmoid activation function is 1 by 1 plus e power minus x. So to draw the graph, I have taken the x values from minus 5 to 5 and placing these values in this formula, I am getting these outputs. So after plotting those values on the graph, I am getting the shape of the sigmoid activation function is like S. And generally the sigmoid activation function is used in the output layer, like it is useful when it is a task like for binary classification, like when a model requires binary classification like frontal, non-frontal, cat, dog, boy, girl. So for only binary classification we can use sigmoid activation function and we can see the derivative of a sigmoid activation function. Generally these activation functions plays important role in forward propagation, but the derivative of this activation functions plays important role in the back propagation. So during the back propagation, the derivative of the activation function is used to calculate the loss with respect to the weights of the neural network, so that model can adjust those weights to minimize the error in the prediction. So here we can see the derivative of the sigmoid activation function. The derivative of the sigmoid activation function is f dash of x is equals to f of x into 1 minus f of x. For the graph, I have taken the values of x from minus 5 to 5 and substituting these values in this formula, I am getting these values. After plotting the values in the graph, I am getting the shape of the derivative of the sigmoid activation function is bell. Now here we talk about the tan h activation function. The range of this function is from minus 1 to 1 and the formula of tan h activation function is e power x minus e power minus x by e power x plus e power minus x. And for the graph, I have taken the values of x from minus 5 to 5 and I am getting some output values. It is the graph of the tan h activation function and now we can see the derivative of the tan h activation function. So the derivative of the tan h x activation function is 1 minus tan h of x square. So for the graph, I have taken the values from minus 5 to 5. Substituting in that formula, I am getting some values. So the derivative of the tan h activation function is like this. Now here we talk about the ReLU activation function. ReLU stands for rectified linear unit and it is one of the mostly used activation function in the hidden layers and the range of this activation is from 0 to infinity. The output of this ReLU activation function is always non-negative because it producing the output in the range between 0 to infinity and the formula for the ReLU activation function is max of 0 comma x. It means if the input x is positive, the output is x. If the input x is negative, the output is 0. Here you can see that whenever I am taking x is equals to minus 5, so here x value is minus 5 which is negative. So the output it producing is 0. And whenever I am taking x is equals to 5 which is the positive value, and it is giving the output value as 5. And the graph of the ReLU activation function is this. You can see the derivative of the ReLU activation function. So the derivative of the ReLU activation function is 0 when x is less than 0 and 1 if x is greater than or equal to 0. For the graph, here are some values I have taken and substituted here, and I am getting the graph of the derivative of the ReLU activation function is like this. And next we talk about the leaky ReLU activation function. Leaky ReLU activation function is a variant of ReLU activation function. This function is introduced because in ReLU activation function we can see that whenever the input to the neuron is the negative values, the ReLU activation function simultaneously generate the output values of 0, which may leads to the neuron dead. So the neurons in the neural network will not update their weights during the training. To overcome this problem, leaky ReLU was useful. So instead of making the neuron dead, it will give a output of some value instead of making it exactly 0. So that can helpful for the neuron to update its weights during the training. So the formula for leaky ReLU activation function is max of 0.01 into x comma x. It is a small alpha value and the range of this function is minus infinity to infinity. Here you can see the input is minus 1, which is a negative value. If we see in the ReLU activation function, the output the ReLU gives as 0. But in leaky ReLU, you can see this value is multiplied with 0.01 and the output the leaky ReLU is giving as minus 0.05 instead of making it 0 as we see in the ReLU activation function. Here are some values and the output of these are these, and the graph for the leaky ReLU activation function is like this. The derivative of the leaky ReLU activation function you can see here. If x is less than 0, the output will be 0.01, and if x is greater than or equal to 0, the output will be 1. Here you can see the graph for the derivative of the leaky ReLU activation function. And now we talk about what is softmax activation function. Softmax activation function is used in the output layer of the neural network for multi-class classification, and the range of the softmax activation function is 0 to 1, and the formula for softmax activation function is e power xi by summation of j is equals to 1 to n e power x of j. And for the graph I have taken the values from minus 2 to 4 and substituting these values in this formula. Here you can see the value substitution and the output values, and placing those output values on the graph, I am getting the shape of the softmax activation function is like this. And the derivative of the softmax activation function is softmax of x of I into 1 minus softmax of x of I. For the derivative graph for the softmax activation function, I am taking the values of x is equals to minus 2 to 4 and substituting these values in this formula. I am getting some output values and plotting those values in the graph. I am getting the shape like this of the derivative of the softmax activation function.